let's get into pure rotational spectroscopy. All right. So the key molecular property in rotational spectroscopy is the moment of inertia given by mr squared. Okay. And so if a molecule doesn't have any moment of inertia, then it doesn't have a rotational spectrum. Okay. And so you also notice here that I've given this as a sum, and that's because for a very simple object, such as two masses on a spring, there will only be one moment of inertia. However, for more complicated looking molecules, there will be multiple moments of inertia. So we'll have a sum there. And I just want to kind of describe this briefly. We have linear rotors. And so HCl is our classic example of a linear rotor. Okay, so examples are HCl, something like CO2, right? So linear molecules. So it doesn't just have to be a diatom. It could be something like carbon dioxide as long as it's linear. And the important thing to note with linear rotors is you get, if you think about the moments of inertia that this thing can have, okay, so if it spins like this, round and round and round about that bond axis, there's no moment of inertia there, right? It's just spinning round and round and round. It doesn't look like anything has happened, okay? However, if it spins this way, there is a moment of inertia there, particularly if one of these masses, well, definitely if one of these masses is bigger than the other, right? As that mass swings around, that's going to create a moment of inertia, okay? And so, of course, if we swung it around the other way, right, we would also get another moment of inertia there. So we say that there's two equal moments, okay, given by mr squared. Now, in the case of getting into more complicated molecules, we're not going to get a straightforward mr squared. It's going to be a little bit more complicated. We're going to have to consider these angles, so there's going to be a cosine dependence there. And I don't want to get into those details. But what I want to point out with these symmetric rotors, the way we can start thinking about how many moments of inertia there are is if I look at an XYZ coordinate, all right, Z, X, Y, and I really start thinking about how I can rotate this molecule based on this coordinate system. Well, you notice here, if I rotate it just around this Z-axis, that's going to create a moment of inertia because of these masses that are swinging around. And we call that the I parallel. And then also, if I rotate around these axes, okay, both of those are going to be equal. So now you have to imagine the green atom there, tumbling over this way or tumbling over this way, right, between X and Y. So those two are equal. And so we call those I perpendicular, okay? So we have two equal moments and one different moment. And so good examples of these symmetric rotors would be like NH3. And NH3, because it has that lone pair on top, right? CH3Cl, right? You could probably have come up with that based on this picture. So I realized I got my two pictures backwards here. So the water molecule is an asymmetric rotor. This methane molecule is a spherical rotor. So I mixed these two things up. And the important thing to note with spherical rotors, there are three equal moments of inertia, right? So if I rotated about that axis, if I rotated about that axis, or if I rotated about that axis, those would all be the same. And so as you might imagine, something like, methane, or even we could add something with non-tetrahedral geometry, SF6, you know, it would be another great example of a spherical rotor, right? Something that's symmetrical all the way around. Okay, so I know a symmetric rotor, you might think, well, why not SF6? And so the important thing with the symmetric rotor is it's got one symmetrical axis. The spherical rotors have 3 symmetrical axes, okay? And then so finally, the asymmetric rotors, such as water, as you might guess, all 3 of those moments of inertia are not equal. Okay? So I'm not going to spend a whole lot of time like getting into all of these specific examples and coming up with these equations. It's important to note, though, that when we think about the rotational spectrum, and I'll note that that is the microwave spectrum, right? Hopefully we remember from our review of StetMech that rotations occur under microwave frequencies. So we can use a microwave frequency to stimulate a rotation. And that's exactly what your microwave does to heat up food. It actually causes H2O to rotate. And in a condensed medium, so molecules don't like to rotate when they're liquids or solids, so it builds up a lot of excess heat. Okay, so moving